What's going on, guys? My name is Hussein, and I want to take a few minutes to explain the difference between a sequential table scan, an index scan, and a bitmap index scan, which is something specific to Postgres. But regardless, it's very, very clever, and I want to take a few minutes to explain the difference between the three. Uh, you're familiar with the sequential table scan as full table scan, but that's just a Postgres terminology. How about we jump into it and play with this a little bit? So I have a table here called grades, and it has an ID, which is a primary key, and it's a auto increment, a serial. I have a primary key, which is an index. I have an index on the ID field. It's just a 1, 2, 3 incremental value. I have a name, which is not index or anything like that. I have a grade field, G, which indicate this is, think about this like a grades of students, right? And G is a value between 0 and 100. And there is an index on the grade field that includes as a non-key value also the ID field, which is pretty something we talked about in many videos, right? So now what I want to do here is explain many aspects of how can I query this table to retrieve certain data. And pay attention to this. I'm going to do an explain because I don't really interested in the result. I just want to know what Postgres is about to do when I want to execute this query. So I'm going to select name, the name of the student from the grades where ID is equal 1,000, right? Where there is a specific ID. And the moment you do that, you can see that the Postgres is going to use an index scan using the grades primary key, which is the ID, and then provide the values using the index condition on the index. That's the ID equal 1,000. And it's going to pull, we know that it's going to pull one value, right? And that explains it why we have one row. Once we pull that row, now the index is responsible to go back to the table to bring the name field. Why? Because the name is part of the heap. It's part of the table, which is part of the heap, right? Which is another data structure. The index is a different data structure. But now, if I do this, for example, so it's like less than, let's say 100. So I'm bringing around 99 value. So Postgres still decided to do an index scan. So what happened here? Let's go through exactly what happened. So we brought 98 rows in this case. What Postgres did, it says, okay, you want anything, any student that has an ID less than 100, which is kind of a silly query if you think about it. What the database decides says, okay, I'm going to use the index to do an index scan on the ID index, and then go scan one by one and find anything that is less than 100, right? And that's very quick to do in a B3, especially that the Postgres kind of have a clue of how many rows is going to get back, right? It says, okay, I want anything that's 100. Anything that's greater than 100, just toss it away. And so it knows that it's going to get values 99 or less because maybe something was deleted. And as a result, it used an index. And for each value that it finds the page where that row exists and goes back to the heap to pull that page, which kind of have one or more rows, and then pulls that value. And this is called random access. So for 99, it went to the page, went to the heap, pulled the row. It did that for 98, for all the rows. Okay, so this is called random access. So you can see that this can get slow if you have a lot of rows. So let's go do something ridiculous. By the way, I have around 50 million rows in this table. So I'm going to do ID greater than 100. Postgres actually is smart enough to know, okay, I expect that this table, this query is going to be insane. So look what that database did here. It says, okay, ID is greater than 100. I have, what is the maximum ID? It has them statistics, right? And I calculate this as a statistic by doing analyze grades. And when you do analyze grades, it will calculate some statistic on the table. It says, okay, this table has like 50 million and this guy wants anything that's greater than 100. That's going to bring 50 million rows back. Is that 50 million? Sorry, 5 million, right? I forgot how many rows I have in this table. So 5 million. So it's going to bring all of those puppies back. Well, wait a second. Scanning the index And every time I find a row in the index that satisfy ID greater than 100, which guess what? Almost all the rows will satisfy that, except the 100 that is less than the 100, right? I'm gonna go and jump. That is extremely expensive to jump back and do a random access. So the Postgres decided to do a sequential scan. What was that? Sequential scan. And says, you know what? Let me just jump to the table and do a sequential scan on the table itself. It's way cheaper to do a sequential scan, full table scan on the table itself. Okay, and pull the results. Now we have two things. If Postgres saw that you have few rows, it's going to use an index scan. If it thought that it's going to have a lot of rows, it's going to say, you know what, it's way cheaper for me to do a sequential scan on the table because I'm going to go there anyway. I don't want to jump, read the index and then read the table. That's expensive, right? So if I'm reading the table and the index all the time, might as well just go and read the table fully, right? That's easier. So now the compromise between the two is when you have a case where you don't have a lot of rows, you don't have a lot of rows so that justifies a full table scan, but you have quite enough that it's actually efficient to use the index. So what Postgres does is actually does a bitmap scan. Let's go an example of a bitmap scan. A bitmap scan is when you do something a little bit slightly less ridiculous, like give me the grades that are greater than 95, right? It's like Postgres doesn't really know how much, but it knows it's a lot. But since there is an index on G, which is the grades, it's worth doing an index scan. But doing an index scan and jumping to the table all the time for every value I find is expensive. So it's going to do instead something called the bitmap index scan. Let's talk about that a little bit. So the bitmap index scan, and you're going to see something, some graphics that I put on the video here, where Postgres is going to build a bitmap, and it's basically an array of bits, and the values represent the page number. So bit number 0 is page number 0, bit number 1 is page number 1, and so on. Okay, until the total number of pages that is in this relation or this table, grades in this case. Okay, so what the Postgres will do, it will do a scan, a bitmap scan on G, and it says, well, you know what? When I find a value that satisfies this condition, I'm going to do an index scan. This is a normal index scan, but I'm not. And when I find something, I'm not going to jump directly to the table. When I find a page, no. I'm going to set a bit on that bitmap. So for example, let's say I found a row, right? And that row belongs to page number 9. So I'm going to go to that bitmap and set bit number 9 as 1. That means, hey, by the way, I found a row that on page 9. And then goes and grew all of the index. It scans the whole index. You have a beautiful bitmap that you can use to jump once to the heap table and pull all these pages. Okay, so that's what we're gonna do right here. Now we're gonna do a bitmap heap scan. So using the number of pages that I know exactly to fetch, I need to jump to the heap once and fetch all those pages. Okay, and when I fetch all those pages, guess what? Every page is gonna have one or more row, right? That's how Postgres stores things. Guess what? Some of those rows will not satisfy the G greater than 995 criteria. So the Postgres does a recheck on the condition only to filter out the rows that has been filtered and drops the rows that have been filtered. In this case, we were lucky that the exact number of rows actually fit exactly in the pages, right? So that's a bitmap index scan. So this is very, very interesting, guys. So let's spice things up a little bit. With a bitmap and scan. So the beauty of the bitmap index scan is you can scan multiple indexes or indices from the UK. You can scan multiple indexes, build those bitmaps, add them together, and then get one beautiful bitmap and then jump to the heap. Let's take an example. I'm going to do an explain where grade is greater than 95 and ID is less than, 10,000. When I do that, look what happened here. ID has an index and G has an index. So what Postgres it did an index scan, a bitmap index scan on G, and calculated that beautiful bitmap that we talked about, and did another bitmap scan on grades primary key, which is the ID field, and then now I have two bitmap. What it did, it just ANDed them. You know how smart this is, guys? By ANDing them, any page that exists in one and doesn't exist in the other, I don't have to visit it because 100% that row is not going to satisfy my criteria. This is genius. So all of a sudden, instead of having 9,000 rows and whatever this thing, 20,000 rows, you're only going to fetch 394 rows. Beautiful. And then once we have this beautiful final thing, you go to the heap, we do a bitmap heap scan this time with this final result and the result, and then go and do a recheck. Why? Because you have to do a recheck because you're fetching some pages, some rows on those pages that you're fetching might not satisfy your criteria. So you're doing a recheck again on those things. That's not so expensive because once you fetch a page, you get those rows for free in memory, hot, right? In the shared memory to be specific. All right, guys. So that was table scan, full table scan, sequential scan, index scan, and bitmap index scan and bitmap heap scan. Hope you enjoyed this video. I'm gonna see you on the next one. You guys stay awesome. Goodbye.